Hello, my name is Alison Davis. I am an associate engineer at Jensen Hughes, and today I will be going over a railcar operational environment evacuation study that was performed. I would like to also acknowledge my colleagues Manuel Daza and Anil Kapahi for their assistance on this research effort. So a brief outline of what I plan to present. First, I'll be going over the motivation for this research effort, then the literature review that was conducted. Then we'll be looking at the egress model development and the modeled scenarios and the associated results. And then lastly, the conclusions and recommendations of this research effort. The motivation for this research is due to the differences in egress from a rail car versus typical commercial buildings. When egressing from a rail car, occupants can experience highly congested environments and also have unique considerations like navigating through tight aisles within the rail car itself. The goal of this study is to understand egress from a rail car in a tunnel and in a station using Pathfinder, and to quantify the impact of the operational environment by looking at relevant input parameters. A literature review was conducted, first looking at Fruin's Pedestrian Planning and Design Guide. Fruin introduces the level of service concept, which considers density effects and how that impacts speed. So Fruin's level of service A here considers a low density of occupants, and as we go up, we can see level of service F considers the highest density of occupants. The Pedestrian Planning and Design Guide is the basis for data utilized in industry standards, specifically the sources shown here on the screen. The results from these inputs will be used to inform the parameters studied in this model and will be further explained later in the presentation. After conducting a literature review, we were able to begin developing the model itself. So we utilized the Pathfinder version shown here on the screen. Additionally, we looked at the Monte Carlo method and used the Monte Carlo method within this analysis. Pathfinder is a deterministic model, meaning that if you run the same input parameter or same file multiple times, you'll get the same results. So the Monte Carlo method was used to vary a specific parameter and see the impact on occupant decision-making and occupant movement as a whole. We also use steering mode. Steering mode is used to try to mimic human behavior as much as possible and considers things like collision handling, occupant interaction, and local density effects. So now we'll look at where the models are, where the occupants are going to be located within the model. So first, looking at the railcar geometry here. There are 6 rail cars located, or 6 rail cars that make up each train. So if we zoom in on this image here, we can see a single rail car. There are rooms that are created to represent the occupant seat location. We can see one of the rooms here, and the occupants are represented by those blue circles. There are 92 occupants per rail car with a total of 552 occupants per train. And we can see the entire 6-car length train here on the bottom of the screen. Something to note is that when modeling railcar egress in Pathfinder, it is recommended to reduce or click the option to reduce diameter to move through narrow geometry when capturing the movement through those narrow aisles. The first operational environment that we looked at for this study was the tunnel. The tunnel geometry is based on NFPA 130 requirements. We're going to be looking at one train within the tunnel. This train is located equidistant between 2 exit doors that are located 800 feet apart, which you can see in this first image here on the screen. If we zoom in on this image, we can see the rail car here, but also the platform. So the platform itself the occupants will use to traverse to either of the exit doors has a width of 44 inches. The second operational environment that we looked at is the station geometry. This is also based on NFPA 130 requirements. The station itself has 2 trains located in the station, so 1 train located on either platform. If we're looking at the platform level, so this first image here, and we're looking at it from the top down, we can see that there are 8 stair and escalator sets that allow the occupants to traverse from the platforms to the concourse. So these stair and escalator sets are highlighted here on the screen. So if we kind of look at the entire station as a whole, we can see this kind of 3D view of the navigation mesh that was created in Pathfinder. We can see that platform level that goes up to the concourse, and then that goes to the north exit here or the south exit. And if we zoom in on that north exit, you can see that that consists of an escalator, a stair, and an escalator here. Something else to note is that we're going to consider maximum occupant loading within this geometry. So there's going to be 552 occupants waiting on either platform. An additional 552 occupants will be located on platform 2 to account for missed headway due to disruptions and delays. And this guidance was found in NFPA 130. So in general, there's going to be about 2,700 occupants located within the station. So now we're going to look at the scenario matrix of what was run for this analysis. So the key parameters that we highlighted are going to be walking speed, occupant diameter, occupant height, and occupant boundary layer. So if we look at the walking speed in particular, what is highlighted, or excuse me, what is in green and bolded on the screen is what's going to be varied for each simulation. So we can see that we're going to be looking at the Pathfinder default value for walking speed. We'll be looking at a normal distribution of walking speed based on Fruin, a simplified distribution. This is also going to be based on Fruin's work, and then the NFPA 130 default walking speed. And then when looking at varying the other parameters such as diameter, height, and boundary layer, we can see those parameters once again bolded and highlighted in green here. We have a variation in the diameter that we'll be looking at, a variation in the height, and a variation in that boundary layer. Something to note also is that when looking at the additional parameters, we're going to be analyzing those when utilizing the maximum walking speed from Pathfinder, so that 3.9 feet per second default. And then we'll also be looking at the parameters when using the simplified distribution for walking speed. And then lastly, we're going to be looking at varying all the parameters at once to represent something more realistic, and that's going to be utilizing all these parameters highlighted and bolded in green. So we are not going to be looking at the NFPA 130 walking speed moving forward in any of this or in this research. So this is because diagnostic models were run that showed that the average egress time when using the NFPA 130 walking speed was 117% greater than the walking speed when using that Pathfinder default value. NFPA 130 speed accounts for a high density of occupants, which equates to level service E or F. You can see if we kind of look at that high density of occupants that the NFPA 130 walking speed on the corridor is indicated by the star here on the screen. So that NFPA 130 walking speed of 2.06 feet per second yields unrealistic results and is not recommended for use in Pathfinder because Pathfinder uses the default walking speed of 3.9 feet per second and then incorporates localized density effects and reduces the speed accordingly based on the algorithm in Pathfinder. So incorporating a default walking speed that considers a density reduction is overly conservative and is not recommended. So we started with running a base case for the station and noticed something interesting with the egress from occupants. So in general, we're going to assume that escalators shut down upon fire alarm evacuation. So the escalators that are modeled in Pathfinder are going to be treated as stairs. Occupants will just walk up those as normal. So as we can see here listed on the screen for both the north and that south exit, we can see that occupants are not equally distributing between the means of egress. We have occupants that are utilizing this escalator here, this stair here, but the escalator that's highlighted in red is not being utilized. So we needed to consider parameters that factor into cost and how this is going to impact occupant decision making. It was determined that the current room distance penalty is the parameter that we wanted to look at to kind of fix this issue that we were seeing in Pathfinder. The current room distance penalty is a basic implementation of fatigue, where occupants are preferring shorter distances over shorter times, the greater distance they travel within a room. So the default value for this parameter is 35 meters, and it is recommended to change it to 0. When it's changed to 0, this eliminates decision-making as a function of the concourse length, and we can see the impact of changing that parameter in this table here. So if we utilize the default values, we can see how occupants distribute between escalator 1 and escalator 2, which will be referred to in this image here. So we can see that that default parameter has an uneven distribution for the north escalator. We have about a 9 and 91% variation there. And then if we go to the south escalator, we can see that that distribution is once again uneven. We have a 30 and 70% distribution. When we change that room distance penalty to 0, we're getting an even or a relatively even distribution between both escalators, close to a 50-50% distribution. And we can see here in this image that occupants are visually also using both of those escalators. So after establishing the proper inputs for the station, all of the scenarios were run and the data is presented here. So something to note is that the minimum egress time, average egress time, and maximum egress time presented in this table considers the 25 Monte Carlo runs that were performed. So the way to analyze parameter impacts are by looking at the variations in the data. The minimum and maximum variation is calculated as shown here. And this helps to inform the impact of the Monte Carlo analysis on this study. The second variation is the variation relative to the default value, and that is calculated as highlighted here. This helps to determine the greater impact of a specific parameter. And something else to note is that we have different formulas that are being used when looking at the default speed and the impact on the parameter and the simplified distribution indicated by SD here. So we can see those different formulas highlighted for proper comparison. So first we'll be looking at the individual variation within walking speed. What we have here is showing the minimum, average, and maximum egress times for the tunnel on the left, and the same thing shown for the station on the right. When looking at the tunnel, we can see that there is a 17% variation in the total egress times with the default Pathfinder inputs, and we can see that there is a 3% expected variation for the station here when utilizing the default values as well. So this here is highlighting the importance of performing a sensitivity analysis and the environment itself, because you can either over or under predict the total egress time based on the percent differences that are shown here on the screen. A similar conclusion can be drawn for both operational environments utilizing the other walking speeds that were analyzed, which are the Fruin normal distribution and that simplified distribution of walking speed. So now to narrow in on the impact of a specific parameter, we're going to be looking at the default versus scenario average, specifically for walking speed. So we have highlighted the variations that were shown in the previous table, again here on the screen. In general, the total evacuation time is going to be driven by the slowest person in the group. So when utilizing Fruin's normal distribution of walking speeds, 50% of occupants are moving at speeds less than that mean value. We have an average walking speed of 4.2 feet per second when utilizing the simplified distribution, which is faster than that Pathfinder default, which makes sense why we're seeing this negative variation shown in the table. We can see, though, that there is a large variation within the Fruin walking speed distribution for the station in particular. So we're going to look at why that impacts the station more. So if we look at this image here on the left of the screen, we're seeing the occupant egressing with the default Pathfinder walking speed from the platform level to the concourse. So as they're moving up the stairs with that default speed, they're able to move at a constant and steady speed, and then they're able to continue that constant speed on that level concourse as they move towards the station. With the Fruin, however, we have fast occupants that can get stuck behind slow occupants on the stairs, which really reduces the speed at which occupants can egress the space. The only time that occupants are really able to make up for that kind of reduction in speed and getting stuck behind those slow occupants is when they're on the level concourse and they're able to navigate around those occupants. And you can kind of get a visual representation of this in the sense that these occupants represented by these cylinders here are having a staggered effect as they move towards that station exit. And then also we can see that there is a larger variation in the through and walking speed distribution for the station compared to that of the tunnel, which we'll further explore. So these videos here are going to show the egress from the rail car in the station on the left, and you can see that there's queuing that's occurring at these stair locations where we have egress from the tunnel on the right, and you can see that there's kind of relative free movement within that platform or within the corridor. To further quantify the impact of the operational environments, we're going to look at the time series evacuation data. So we have the tunnel data here on the left of the screen and the station data here on the right. We can see that before occupants leave the rail car, which is indicated by these vertical dashed lines, you can see that the speed at which they're walking is relatively constant and relatively slow for both the default, shown in blue, and the Fruin distribution, shown in orange. And we can see similar results for the station as well. We see a constant and kind of slow speed before they're able to egress or get out of that rail car, once again indicated by these vertical dashed lines. The tunnel is driven by, or the egress within the tunnel is driven by the congestion within the rail car. So once they're able to get out of the rail car, they're able to reach the unimpeded assigned walking speed. So you can see with that default value, they're able to walk at that maximum default speed. And for the Fruin distribution, they're able to walk at a speed somewhere between that minimum and maximum value. Once occupants are out of the rail car for the station, we can see that there's a lot of variability within that speed. We can see that sometimes they're able to reach that max, but we see a lot of variability. And that variability is due to the means of egress within the station. We have the stairs and the escalator combinations. And we have a lot of queuing that occurs and reductions in speed that occur at these locations. So these can be attributed to the greater deviations that we're seeing for the station rather than the tunnel. Now, if we look at the impact of a single parameter, these single additional parameters such as diameter, height, and boundary layer, these are a little bit more intuitive. So the average diameter of the occupant is increased from 17.9 inches to anywhere between 17.9 to 24 inches. So with that average diameter being increased, we're going to impact collision handling and increase the overall evacuation time, which makes sense why we're seeing a positive deviation or variation in the egress times. When looking at the boundary layer, 75% of occupants have a reduced boundary layer, and this is going to increase the walking space these occupants have and allow for more efficient egress, which is going to decrease the total egress time. Height does not have an impact on occupant egress in the environments that were studied, and similar conclusions can be drawn for the effects of diameter, boundary layer, and height when using a simplified distribution for the walking speed. When we look at all parameters and vary all parameters at once, this is to kind of show what would be more realistic of what we would see in a typical train scenario. So we're seeing a similar variation with the tunnel that we did previously, but we can see that there is a reduced magnitude of variation seen when looking at the station compared to the Fruin distribution. And this is because when combining all those parameters, looking at all of those at once, this is more realistic, and we can see that the impacts of parameters like diameter are decreasing the impact of the variability in the speed. So just going to quickly go over the preliminary conclusions and recommendations of this study. Something to note is that the results only apply to the distinct operational environments that we are studying here. In general, we do have recommendations for the input values. We recommend to set the current room distance penalty equal to 0, and we also recommend that you not use the NFPA 130 walking speed of 2.06 feet per second. It is important to perform a sensitivity analysis using the Monte Carlo method. And lastly, we see differences in egress times due to operational environments, and this can be attributed to geometry. Occupants are not able to reach those unimpeded walking speeds until they leave the rail car because of all the congestion that occurs within the rail car. The congestion effects within the rail car propagate within the tunnel, while we see different impacts within the station because we have impacts of the means of egress and queuing in the station that occurs that results in the stochastic walking speeds that we saw. We would like to acknowledge the Federal Railroad Administration for funding this research. We also thank both the FRA and Volpe staff for their feedback and discussions on this research topic. Thank you so much for your time, and if you have any questions, my contact info is on the slide. Thank you.
Okay, I think you can hear me now, right?
Perfect, yes.
All right, hey, welcome. Thanks for joining us.
Hi, thank you.
Great talk. We're going to go ahead and see if we have any questions in the room. Anyone? See a lot of fascinated faces, but, oh no, that's just the light. No, a lot of smiling faces. Rayshawn? So Rayshawn has one here.
Hello, can you hear me? Oh, yep. Alison, thank you for your presentation. Quick question about the room distance penalty. How did you iterate from the default down to the value of 0?
Yeah, so when I was looking into kind of the impact on how the occupants are using that escalator, I kind of just went through and did just an iterative process. So I first started by actually increasing that room distance penalty and kind of just, going up by like a systematic amount and increasing that penalty. And kind of once we got to a certain amount, which was basically like the length of that concourse, the results that we were seeing were essentially the same as if we turned that room distance penalty to 0. So in order to kind of make that a overarching kind of recommendation that's independent of the concourse length, we reverted back to that 0 value, but it was first started by doing a systematic increase and iterating through just larger default values or larger values in the default.
And to be clear, that 0 essentially disables the penalty. So it's not like it's a 0 length, or 0 penalty. It just disables the feature altogether.
Right.
The other Brian from Thunderhead here. And just a comment on that room distance penalty. I think in your case, since everybody's essentially evacuating in one direction, it's less relevant. That was introduced to handle large rooms, which you must have had a large room just connected to the escalators. Yes. Generally in buildings, to keep the occupant from bouncing back and forth as they see, oh, it's 2 seconds faster on the east, 2 seconds faster on the west, 2 seconds faster on the east. And so it's kind of a balance between room size and that parameter, depending on what behavior you're looking to model. And that I would just add that another potential thing you can do in that situation is if you created sort of a lobby room, even if it's just a door across the entire width, just prior to where you want the agents to make the decision, then the room penalty doesn't really come into it because they're in a small room and they'll make their decision in a smaller room. So anyway. Yeah,
that's a great point. That's another thing that we kind of considered looking at, but instead of like breaking up the rooms and impact or changing the geometry of the space, was more so focused on what can we change in the parameters in the model. But yeah, that's a really good point.
Any other questions?
There is a question here through chat, or I guess Q&A. Amazing study and presentation. Can you please advise if you have considered disabled passengers in the model, or considered disabled passengers, and what was the assumed speed for them and for the assistant personnel?
Yeah, so that's a great question. So we actually, for this study, just considered able-bodied individuals, kind of just that way we could specifically isolate those parameters that we were looking at, specifically focusing on walking speed. But I guess you can kind of say that in the normal distribution of walking speed that we looked at, because there's like that low and high end range, that lower end of the normal distribution, that slower walking speed can kind of inherently capture those mobility impaired occupants, but it wasn't explicitly studied in this analysis.
Great. I don't see anything else in chat. Oh, there's more? Hey, they're coming in. All right, Eric Greenwald, great presentation. Did you take into consideration an escalator out of service for repairs and not available?
Yeah, so for this analysis, we considered every escalator being available. So we didn't, like I mentioned in the presentation, we didn't consider the escalators actually being used as escalators in the model. We did consider them like turned off and occupants just walking up those as they would stairs, but we didn't consider that there would be any exits that were out of service. So we considered them being able to use all 8 stair/escalator combinations, but they were all being used as stairs essentially.
I see. So a full capacity, full capability anyway, just in stair mode. That makes sense.
Yes. Yeah.
Anyone else? No? Okay. I don't see anybody else in here. And nothing else through Q&A. So thank you for joining us. Thank you for the talk and the presentation.
Awesome. Thank you.
We look forward to more work in this area. There must have been a big project dealing with fire and tunnels and trains and egress. It's kind of a theme emerging from Jensen Hughes too. So a lot of work in this area. It's good to see. So again, thanks, and we'll see you soon.
Awesome. Thank you. Yep. Thanks.